Welcome to the Deep Dive. Today we're taking a high-speed tour of our own solar system.
We've gone through a huge amount of material, all centered on this theme of ancient worlds, new discoveries.
And our goal here is to give you a really solid foundation on what makes our planetary neighborhood tick, from the raw power of the sun to some really surprising discoveries about water and life.
The mission is basically to get you up to speed on the most revolutionary findings, because the picture of our solar system has changed so much, even in just the last decade.
So let's start with something that, you see all the time but maybe don't think about.
Right.
Why do we see pictures from NASA where the sun is glowing green or Mars has these patches of electric blue?
I think that's a great place to start. It's a concept called false color, and honestly, understanding it is fundamental to, well, understanding almost any astronomical image.
Okay, so it's not what my eyes would see if I were actually there in a spaceship.
Not at all. I mean, think about it. Our eyes can only see this tiny, tiny little sliver of the electromagnetic spectrum.
Visible light, the rainbow.
Exactly. But the universe is just, it's screaming with information in all this invisible light. We're talking radio waves, UV, X-rays.
And our instruments can see that invisible light.
They can. But then we have a problem. How do you show that data to a human brain?
Mm-hmm.
So we assign a color we can see to a wavelength we can't. We might make, say, extreme ultraviolet light look bright green just so it stands out.
Or it's not even about light, it's about data, like methane levels or something.
Precisely. You could color code high methane concentration on Mars as red and low as blue. It's just a way to visualize information and make it clear. It's a tool.
A really important tool to remember. Okay, so with that in mind, let's jump to the absolute center of everything, the sun. We call it a yellow dwarf, but that name is pretty misleading.
It really is. First off, if you were in space, the sun would look brilliant white. The yellow and orange colors we see are purely an effect of Earth's atmosphere scattering line.
At sunrise and sunset.
That's right. And as for the dwarf part, well, technically it is, but it's still bigger and brighter than about 85% of all the other stars in the Milky Way.
Which is just staggering. And it's responsible for, what, 99.86% of all the mass in the entire solar system?
It is. It's this enormous ball of hot plasma and magnetic fields, and at its core, it's constantly performing this incredible act of fusion.
Right. So basically every single second.
Every single second, it takes about 614 million metric tons of hydrogen and fuses it into 609 million tons of helium.
And that 5 million tons that just disappears, that's the energy.
That's the energy. It's converted instantly into gamma rays, which bubble up and become the light and heat that makes life possible. It's that whole "we're made of star stuff" idea, made real every moment.
But this engine is not always friendly. It creates something we have to deal with here on Earth. Space weather.
It does. All that energy is tangled up in these incredibly intense, moving magnetic fields, and that creates what we call solar activity.
Like sunspots.
Sunspots are the most visible sign. They're temporary cool spots on the surface caused by magnetic fields poking through, and they come and go in a roughly 11-year cycle.
But when those magnetic fields get really twisted up and then they snap.
That's when you get the big stuff. You get solar flares, which are just massive bursts of radiation. And even more dramatically, you get coronal mass ejections, CMEs.
And a CME is basically a chunk of the sun flying at us.
It's a huge cloud of charged plasma, blasted out at speeds up to, well, over 1,000 kilometers per second.
So if a big one is aimed right at Earth, what does that mean for us on the ground, beyond getting a nice aurora?
Well, our planet's magnetic field is a pretty good shield against a solar wind, which is the constant stream, and most CMEs. But a direct hit from a big one, it can overwhelm the shield.
And cause, what, power outages?
Widespread blackouts,
Yeah.
It can induce these huge currents in our power grids and just overload them. And it can completely fry satellites, which means your GPS, your phone service, it could all go down.
Which is why we have missions like NASA's SDO, constantly watching the sun. We need a warning.
We absolutely do. Okay, so let's move in from that giant furnace to the inner rocky worlds. Starting with the planet of extremes, Mercury.
Smallest planet, closest to the sun, oldest surface, so you'd think it would just be a baked, dead rock.
You would. Which is why the biggest surprise from the Messenger spacecraft was finding evidence of water ice.
Water ice on Mercury? How is that even possible?
It's because Mercury barely has a tilt. So at its poles, there are these deep craters where the bottom has never seen a single ray of sunlight. They are permanently shadowed and cold enough to trap ice for billions of years.
Incredible. And you can also see its violent past, right? Like the Caloris Basin.
Oh yeah, that's one of the biggest impact basins in the whole solar system.
Oh.
And those false color images show these orange splotches that suggest, huge lava flows from ancient volcanoes.
So from the roasted planet to what some people call Earth's twin, Venus.
A twin that went down a very, very different path.
An understatement. I mean, Venus isn't just hot, it's a hellscape. The temperature is over 400 degrees Celsius, enough to melt lead.
And the atmospheric pressure is almost 100 times what it is here. You'd be crushed instantly. And the clouds are basically concentrated sulfuric acid,
What happened there?
a runaway greenhouse effect. It seems like massive volcanic eruptions about 700 million years ago just pumped the atmosphere full of CO2, and it never recovered.
So given all that, why are astrobiologists even remotely interested in looking for life on Venus?
Well, the surface is a definite no. But if you go about 50 kilometers up into the atmosphere, the temperature and pressure are actually surprisingly Earth-like
In the clouds.
in that stable cloud layer. So the speculation is, could single-celled organisms, maybe some kind of microbes, be floating up there feeding on the sulfur chemistry? It's a long shot, but it's a fascinating one.
Okay, so let's come home to Earth and our moon.
Our perfect little oasis with its thin atmosphere and that protective ozone layer, and our moon, which has a pretty dramatic origin story.
The giant impact theory.
That's the one. The leading theory is that about 4.5 billion years ago, a Mars-sized object slammed into the very young Earth.
And the debris from that collision formed the moon.
Yep, it coalesced incredibly quickly, in maybe just a month. And what was left on the surface were those dark patches you can see, the lunar mare, which are just vast plains of basalt from ancient lava flows. And just like Mercury, it has ice hidden in those dark polar craters.
Fascinating. Okay, let's move outwards to Mars, the red planet, where the mantra for decades has been follow the water.
And boy, have they found it. I mean, after we got past the old ideas of canals, the evidence for a wet Martian past just started piling up.
What are some of the biggest finds?
Well, we found patches of water ice near the North Pole that stick around all year. We found minerals like hematite that on Earth almost always form in water. The Phoenix lander literally scraped up subsurface water ice.
It even saw snow falling.
It did. But the single biggest mystery on Mars right now, the thing that keeps scientists up at night, is methane.
Methane gas. Why is that so exciting?
Because on Earth, methane comes from two main sources: geology, like volcanoes, or biology, microbes.
And we're seeing it on Mars.
We are. And not just that, it appears in plumes seasonally. It spikes in the Martian spring and summer and then disappears.
So the big question is this some kind of geological process we don't understand yet? Or could it be, something alive under the surface, burping out methane?
That is the multi-billion-dollar question.
Yeah.
And we can't forget Mars's weird little moons, Phobos and Deimos. They're almost certainly captured asteroids.
And Phobos is doomed, right?
It is. Jupiter's gravity is slowly pulling it apart. In about 100 million years, it's going to be shattered and form a ring around Mars.
Wow. Okay, past Mars, we hit the asteroid belt.
Right. The vast collection of debris between Mars and Jupiter, millions of chunks of rock, from dust all the way up to Ceres, which is a dwarf planet.
And these are basically the leftovers of a planet that never formed.
Exactly. Jupiter's immense gravity just kept stirring the pot, so the material could never coalesce into a full-size planet. And it's a constant reminder that these things are out there. An asteroid about 12 kilometers wide is what we think wiped out the dinosaurs.
Now, speaking of Jupiter, the true giant of the system.
The heavyweight champion. It's so massive it's almost a failed star. It has 79 moons and a magnetosphere that is just unimaginably huge.
We all know the Great Red Spot.
But the scale is what's hard to grasp. It's a storm, a cyclone, that's been raging for centuries and is 3 times the diameter of the Earth, with winds at the edge hitting 550 kilometers an hour.
But the really groundbreaking science, the stuff that changes how we think about life, is happening at its moons.
Absolutely, because of a process called tidal heating.
So this isn't about sunlight for energy.
Not at all. Jupiter's gravity is so powerful that as its inner moons orbit, it stretches and squeezes them constantly, like bending a paperclip back and forth.
And that generates heat from friction.
Immense heat. It's what drives Io to be the most volcanically active body in the entire solar system. It's constantly turning itself inside out.
And it's what makes the next moon out, Europa, probably the most exciting place to look for life beyond Earth.
Without a doubt. The theory is that beneath a 20-kilometer thick shell of ice, Europa has a liquid water ocean that's 100 kilometers deep, kept liquid by that tidal heating,
And that heat could create hydrothermal vents on the ocean floor.
exactly like the ones we find in Earth's deep oceans, which are just teeming with life that doesn't rely on sunlight at all. Europa is its candidate number one,
And then there's Ganymede, the biggest moon in the solar system.
bigger than Mercury. Yep. It's also thought to have a subsurface saltwater ocean, and it's the only moon we know of that has its own magnetic field.
So what about the last one, Callisto?
Callisto probably has an ocean too, but it's considered less likely to host life. Its ocean is probably much deeper, and there might be a thick layer of high-pressure ice separating the water from the rocky core, which would cut off that crucial chemical interaction.
Okay, let's keep moving out. To the ringed planet, Saturn.
The jewel of the solar system. And those glorious rings, they look so solid, but they're incredibly thin, only about 10 meters thick on average.
And they're made of ice.
Almost entirely water ice. Billions and billions of particles, from tiny specks to chunks the size of a house.
But again, like Jupiter, the real action is at the moons. Let's start with Titan.
Titan is just bizarre. It's the only moon with a thick atmosphere, and it's like a chemically frozen version of early Earth.
It has liquid on its surface.
It's the only other place we know of with stable bodies of liquid on the surface. But it's not water. It's lakes and rivers of liquid methane and ethane.
It's so strange. But then there's Enceladus, which might be even more promising for life than Europa.
It's a very strong contender. This little icy moon has these tiger stripes near its south pole, which are basically fissures. And out of these fissures, it's spraying geysers into space.
Spraying what exactly?
Water vapor, ice particles, and this is the key, organic compounds. It's basically venting samples from its subsurface liquid ocean directly into space for us to find. It's an astrobiologist's dream.
So it's an accessible ocean. Just incredible. Okay, quickly, the two ice giants way out on the edge, Uranus and Neptune.
Right. Uranus is the one that's famously tipped over on its side, probably from a huge collision long ago, and it gets that blue-green color from methane in its atmosphere.
And Neptune is just cold and windy.
Frigid and whipped by the fastest winds in the solar system, yeah. Supersonic winds. Voyager 2 saw a huge storm there, the Great Dark Spot, but when Hubble looked a few years later, it was just gone.
And Neptune has an interesting moon, Triton.
Very. It orbits backwards, which means it's almost certainly a captured object from further out. And it has active geyser-like plumes, a bit like Enceladus.
Which brings us to that further out region, the Kuiper Belt.
The deep frontier.
Yeah.
This is a huge region of icy rocky bodies beyond Neptune. It's where we find dwarf planets like Pluto and Eris.
So a dwarf planet is just something that's big enough to be round, but it hasn't cleared its orbit of other stuff.
That's the gist of it, yeah. They're part of a larger population of objects out there. And this region is also the source of most comets.
And comets are important because they might be how life got started here.
There's growing evidence for it. The idea is that in the early violent days of the solar system, comets constantly bombarded Earth, delivering both water and the complex organic molecules needed to kickstart life.
Wow. So we've gone from the sun all the way out to the Kuiper Belt. When you synthesize all this, what's the big picture?
I think the biggest takeaway is that our whole idea of habitability has been completely blown open. It's not just about being the right distance from the sun anymore. It's about tidal heating, subsurface oceans, and the chemistry happening beneath miles of ice on moons like Europa and Enceladus.
And the sun's influence doesn't just stop at Pluto. It creates this huge protective bubble around us, the heliosphere.
That's right. The solar wind blows this massive bubble in interstellar space that shields us from the most dangerous cosmic rays from the galaxy. The edge of that bubble, the heliopause, is the true edge of our solar system.
The point where you've officially entered interstellar space.
Exactly. And when you pull back from there, you see our little system is just one of maybe 400 billion star systems in our Milky Way galaxy.
And the numbers just get incomprehensible.
They do. We estimate there are at least 50 billion planets in our galaxy alone, and maybe 500 million of those are in the traditional habitable zone. And some new estimates suggest there might be twice as many free-floating rogue planets, not even attached to a star, as there are stars.
So when you think about that famous pale blue dot photo of Earth from billions of kilometers away,
And you realize our galaxy is just one of maybe 200 billion other galaxies in the universe.
the sheer number of worlds is just overwhelming. So knowing all that, knowing that the building blocks for life are everywhere, the question we want to leave you with is a simple one. Do you think we are alone?